Have you ever wondered how your computer or smartphone can maintain accurate data, even though it's constantly transmitting and receiving information? In a world that's increasingly digital, the integrity of data has never been more crucial. Whether it's a simple text message or complex scientific data, the importance of error detection in digital logic and design cannot be overstated. You see, when data is transmitted or stored, it can be affected by various factors, causing it to change unintentionally. This could lead to serious consequences, especially in critical systems like aviation or healthcare, where a single bit of error can have drastic implications. Moreover, in our everyday lives, from streaming a movie, sending an email, to making a bank transfer, we rely on the accuracy of digital data. And ensuring that accuracy is a fascinating process that involves a blend of mathematics, logic, and design. This is where parity, a simple yet powerful concept in digital logic and design, comes into play. So what exactly is parity in the context of digital logic? Well, in digital logic and design, parity is a method used to detect errors in data transmission or storage. Picture this. You're sending a string of binary code from one place to another. Now, how would you know if something went wrong along the way? If a bit got flipped from a 1 to a 0 or vice versa? That's where parity comes into play. Parity is a simple yet effective tool that involves adding an extra bit to our binary code. This extra bit, known as the parity bit, helps us make the total number of set bits. Those are the ones either even or odd. So you're probably wondering, why does the total number of set bits matter? Well, it's all about consistency. By setting a rule that our data should always have an even or odd number of set bits, we create a pattern. If this pattern is disrupted, we know an error has occurred. There are two types of parity we commonly use: even parity and odd parity. With even parity, we make sure the total number of set bits, including the parity bit, is an even number. Conversely, with odd parity, we ensure the total number of set bits is an odd number. Let's go through a quick example. Suppose we have the binary data 1011. For even parity, if we count the number of set bits, we get 3, which is odd. So we add a parity bit of 0 to keep the total number of set bits even. For odd parity, we would add a parity bit of 1 to make the total number of set bits odd. So there you have it. That's the heart of the concept of parity. It's a way of adding a simple check to our data to ensure its integrity during transmission or storage. Now that we have a basic understanding of what parity is, let's delve deeper into the two types of parity, even and odd. Let's start with even parity. When we talk about even parity, we're referring to a method in digital logic and design where the total number of set bits, including the parity bit, is set to be an even number. Imagine it like this. You're arranging some apples on a table. Now, you have a rule that you must always have an even number of apples on the table. If you have 3 apples, you need to add 1 more to make it 4, which is an even number. If you already have an even number of apples like 4, you don't need to add any more. This is the same principle that even parity follows. If we have a binary code like 1011, which has an odd number of set bits, we need to add a bit to make the total number of set bits even. In this case, the parity bit will be 0. This results in the binary code 10110. Now, if we take another example, say 1001, which already has an even number of set bits, we don't need to add another set bit. The parity bit in this case will be 0, making the final binary code 10010. Remember, the goal of even parity is to make the total number of set bits, including the parity bit, an even number. This parity bit is then transmitted or stored along with the original data. This simple addition of a parity bit can help detect errors when the data is transmitted or retrieved. If upon retrieval, the total number of set bits is no longer even, it's an indication that an error has occurred during transmission or storage. Even parity is a straightforward yet effective method to check for errors in digital communication and storage. It's like a security guard, keeping a watchful eye on your data and raising an alarm if something goes awry. So, with even parity, we're ensuring that the total number of set bits, including the parity bit, always adds up to an even number. Now, let's move on to the concept of odd parity. In digital logic and design, odd parity represents another way to ensure data integrity during transmission or storage. Similar to even parity, odd parity also involves adding an extra bit to our binary code, known as the parity bit. But here's the twist. With odd parity, We aim to make the total number of set bits, which are the ones, including the parity bit, an odd number. Let's dive into an example to illustrate this concept. Suppose we have a binary code, let's say 1011. Counting the set bits, we have 3 ones. Now, 3 is already an odd number, isn't it? So in this scenario, our parity bit would be set to 0. This is because we don't need to add any more set bits to make the total odd. Hence, our final data sequence with the parity bit becomes 10110. But what if our original data had an even number of set bits? Let's consider the binary code 1001. This time we have 2 set bits, which is an even number. To make the total number of set bits odd, we need to add a 1 as our parity bit. Therefore, our final data sequence with the parity bit becomes 10011. The beauty of this method is its simplicity. By ensuring an odd number of set bits, we can quickly identify any errors in the transmission or storage of our data. If the receiving end gets a data sequence with an even number of set bits, it immediately knows that something went wrong during the transmission. However, it's crucial to remember that while parity checks, whether even or odd, allow us to detect errors, they don't provide a mechanism for correcting those errors. For more robust applications requiring not just error detection, but also error correction, we often use more advanced methods, like Hamming codes. In contrast to even parity, odd parity ensures that the total number of set bits, including the parity bit, always adds up to an odd number. Now that we understand parity, where do we see it implemented? Well, let's delve into that. Parity comes into play in various ways. For starters, we have single-bit parity, where a solitary parity bit is affixed to the end of our data. This simple implementation is quite common and efficient. Then, there's block parity. In this case, a parity bit is added to each block or group of bits. Think of it as a meticulous librarian, keeping track of each book or block in the library of data. After transmission or storage, the received data undergoes a checkup, a bit like a medical examination. This checkup, known as check parity, looks for any discrepancies. If the data maintains the correct parity, it gets a clean bill of health, meaning no error is detected. However, if the parity is incorrect, the alarm bells ring, indicating an error. Circuit-wise, parity checking is typically done using XOR or exclusive OR gates for each bit position. Like a vigilant gatekeeper, the XOR gate generates the parity bit based on the set bits in the data. Now, where are these implementations applied? The primary application of parity is error detection in data transmission and storage. It's the security guard of data, ensuring everything is in order. Moreover, parity is a reliable partner for memory systems, helping to detect errors in stored data. It's like a detective, always on the lookout for any irregularities. Lastly, some communication protocols employ parity to ensure data integrity. In this role, parity acts as a quality control officer, guaranteeing that the data remains uncorrupted and true to its original form. So, in essence, parity is quite the multitasker. It's a librarian, a doctor, a gatekeeper, a security guard, a detective, and a quality control officer, all rolled into one. As we've seen, parity plays a critical role in various aspects of digital logic and design, ensuring data integrity. Whether it's helping to detect errors, safeguarding memory systems, or maintaining the integrity of communication protocols, parity is an essential tool in the digital world. Let's summarize what we've learned today. Parity is a fundamental method used in digital logic and design for error detection, ensuring the integrity of data during transmission or storage. By adding an extra bit known as the parity bit to a binary code, we can track the total number of set bits, that is, 1s in our data. We've explored the 2 common types of parity, even and odd. In even parity, we make sure the total number of set bits is even, and for odd parity, it's odd. This is achieved by adjusting the value of our parity bit. We also delved into implementations of parity, such as single bit and block parity, and how they are checked at the receiving end. Using XOR gates, we can create circuits to generate these parity bits. Parity's applications span from error detection in data transmission to maintaining data integrity in memory systems and communication protocols. In conclusion, parity is a simple but powerful tool in digital logic and design, playing a crucial role in maintaining data integrity.